So we got some graph, and we got a gap in our knowledge about this graph. Between 3 and 4 here, so you notice we're being asked about the interval 3 to 4. That's the black box there that we've laid over our graph there where we don't know what's going on. Can we know that this graph includes f of x equals 20? You know, f of x equals 20, that's the same as saying y equals 20, right? So in other words, at some point between 3 and 4, do we know that the graph crosses that line and actually hits a point there? Like, as I'm looking at it, I'm thinking, well, it could be doing all sorts of things in there, yes, but, I mean, no matter what I do in there, aren't I going to hit that same point anyway? Ah, there we go. There could be a hole in there, right? So, I mean, if I was going up and then all of a sudden I just hit a hole there and I kept going, that would cause us a problem, right? Yeah, there could also be a jump. Excellent. Like, it could go on and it could do one of these kinds of things. So there could be a jump there. And that would mean that no, it didn't necessarily hit it. What else could happen between them that would tell us that it actually didn't have to hit that? It's a little bit trickier because of how I drew it. Yeah, there could be an asymptote in there as well. Now, in this case, for us to miss 20, our asymptote would have to be doing something a little bit weird looking. It'd have to be like doing one of these. But it could be hitting an asymptote in there as well. So there could be a hole. There could be a jump. There could be an asymptote. What do we call those three? All three of those fall under the same umbrella. Yep, those are all discontinuities. Now, if I told you that the graph was continuous between 3 and 4, is it possible that it did not hit 20 in that case? If it's continuous, could I miss 20 here? No, we couldn't. And so notice that this idea of continuity that we were talking about a little bit last week, and again, like to bring back since we do have a test coming up and it's going to include our continuity stuff, it tells us then some other information about graphs like this. This particular one is an example of something called the intermediate value theorem, which I'm going to go ahead and have you put into your notes. It's one of these big fancy math theorems that has very niche uses. You won't use it all the time, but we want to be able to see how we can apply what we've learned, like about continuity and stuff, in order to help us know some of these odd little things. Now that you got this in your notes, just to kind of help us see what's happening with this, I highlighted the different variables that they're using to represent different quantities in this. The x values in blue and the y values in red, just to help us see what it's really talking about here. So as we're taking a look at this, we know function f is continuous on the closed interval. So it's continuous at the endpoints as well. And so n is some number between f of a and f of b. Notice our y values. So this is like the 20 in our first problem. There's some number that's between them, and notice it says where f of a does not equal f of b. Because if they're equal to each other, how can it be between them? Another one of those lovely detail-y things about math, right? So then, there exists a number c, so there's some x value in that interval. Notice this is an open interval now, because we know it's not happening at a or at b because it didn't equal a and b. So there's some number between a and b, non-inclusive, where the y value at that point equals the y value that we were trying to figure out. That's really what this is meaning. It's fairly intuitive in terms of as we think about it and look at it, like you saw with that first problem. It's just very detailing in how it actually writes it out and explains it. But that's why you need to have it in your notes so that you can actually see what are all these little details along the way. So then using that, this is the way that this sort of problem gets presented, where same setup, but here we're doing it in terms of intermediate value theorem, where we are told that f of x is continuous on the interval. So we're told that it's continuous all the way from 0 up to 7 here. And what does the intermediate value theorem tell us about what happens between 3 and 4? Well, in our first problem we said, does it equal 20? Does it equal 20? Yes. Is it guaranteed to hit any other points along the way? Yeah. Basically what it means is that it will guaranteed hit every point. We will have a y value for every point in there between our two y values. So at our endpoints, assuming that our two y values there are 10 and 30, it means that it's going to hit every y value between 10 and 30, somewhere in between 3 and 4. So then to really see what it does and doesn't tell us here, here's another situation. So we know our function is continuous again. And knowing that our function is continuous between 1, 5, and 2, 9, between x equals 1 and x equals 2, notice that x equals 1, x equals 2, can we know that the graph reaches each of these y values? So take a look at each of those and decide, does it definitely hit that y value or not? So for the first one, y equals negative 6, can we know that it will hit y equals negative 6 in there?
No.
No. Okay, why not?
It's not between 5 and 9.
It's not between 5 and 9. Okay, so then what about y equals 0?
No.
No. Y equals 4?
No.
No. Y equals 5?
Yeah.
Oh, we got a difference of opinion on that one. Well, notice we do hit y equals 5 at 1. But here we're talking about between 1 and 2. So we're looking at like in the interval 1 and 2 like that. The open interval. So can we know that it would hit 5 again somewhere between 1 and 2?
No.
No. So that's actually a no. See, that's a little bit of a detail that we often overlook with this, but yes, we do need to be looking out for. All right, so what about y equals 6?
Yeah.
Yes, okay. Y equals 7?
Yeah.
Yep. Y equals 8?
Yeah.
Y equals 9?
No.
Good, because now we hit the endpoint. So it's no longer between 5 and 9. It's now outside of that, or at it. All right, what about 10?
No.
Nope. 15?
No.
Nope. Now, question. Is it possible that it hit 15?
Yes. Oh, yeah.
Yes. It's still possible that it hit 15. It's just that we can't look at the information given and know that it absolutely does. But it doesn't rule out the possibility, at least. So then, in doing this, we have to know which functions are continuous. And this is going to be really useful for us to know. And so all of these functions are different ones that are continuous at every number in their domain. And so this is probably worth noting for yourself here. Writing down that we can know that all of these are in fact continuous for every number in their domain. Okay, except for the root if there's an endpoint. Because if there's an endpoint, it's only continuous from the one side at the endpoint. And this information is going to be useful to you because the next thing we're going to be doing is we're going to be looking at some equations and deciding if we can know certain values based on the intermediate value theorem. Well, since the first requirement is knowing if it's continuous, this is going to take care of that first checkbox for any time that we see one of these function types. Is we're just going to know that yes, it's continuous because it's a rational expression or whatever. By the way, are all rationals continuous? Is a rational expression, or a rational function rather, continuous for every possible x value?
No.
Well, since a rational is like an x in a fraction, like 1 over x, is that continuous throughout? No. It has an asymptote. So wouldn't that mean that this violates it? No, because notice it says it's continuous at every number in their domains. Since the asymptote is not part of the domain, that's not violating that. And so it really is a matter of just knowing that it's part of the domain in the first place too. Okay? All right, so here is an equation. And this looks like the sort of thing that we could solve, right? We got x cubed minus x plus 1. Take a moment. How would you find that solution? Now, you're probably finding a bit of challenge here, right? Is this one a nice, easy one to solve?
No.
Not really. And so we end up with a little bit of a challenge ahead of us, is how could we solve such a thing? And when doing something like this, the intermediate value theorem actually can help us out if we kind of have a basic starting point. So we can at least figure out if there is a solution within a certain interval. So here I'm going to go ahead and give you an interval. Like if I sketched out what this graph looked like, I might be able to say, I know it's going to happen somewhere between -2 and -1. And so what we're going to do is use the intermediate value theorem to actually prove whether there whether there must be a root for this function on that interval. And by the way, when I say root, what's that mean? Root is just another fancy term for x-intercept. So in other words, I'm looking to see when f of x equals 0. That's what the root is. So we're going to look to see, is there a root, or in other words, is there a place where y equals 0 between -2 and -1 here? In order to do that, we're going to find the lower bound and the upper bound. So for the first of those bounds, that's going to be happening at the -2. And I don't know at the moment whether that's actually going to be the higher or lower number, but it is the lower bound in terms of left and right. So I'm going to be doing f of -2. So we plug -2 into our equation and see what that gives us. And when we do that, we find that f of -2 is -5. Repeat the process for the upper bound, or in other words, find f of -1. And so when we find the value of f of -1, we get 1. So how does this help us? Well, we found our two values, our f of x values at the endpoints of our interval. Is f of x continuous on this interval from -2 to -1? Remember, after we wrote down what the intermediate value theorem was, we saw, okay, what are the different function types that are continuous throughout their domain? One of them, the first one in fact, was polynomial. And that's what this is. This is a polynomial function. And because it is a polynomial function, yes, f of x must be continuous throughout that particular interval because it's continuous throughout its entire domain. And those numbers and everything in between them are part of this domain. All right, so then, the last question that we really have to answer here is 0 between f of -2 and f of -1. So f of -2, that's what we did over here, right? F of -1, that's what we did over here. Is 0 between those two numbers? Yes, it is. Because of that, we have now met the criteria of the intermediate value theorem. Because that number is between those two y values on a continuous function, then we can conclude that it works. Now again though, this is one of those mathematical theorems. This is one of those things where we have to actually lay it all out. And so when we write our solution, when we write our conclusion for this is what we end up writing out. We say first that f of x is continuous on our interval -2 to -1, remember closed interval there, and that f of -2 is less than 0, and that is less than f of -1. In other words, 0 is between our two y values. Therefore, there exists a value c. Remember, c is just kind of that, we don't know what the x value is, but there's some x value between -2 and -1. There is a value c in that interval where that its y value would be our root, would equal 0. I suggest you write down this conclusion on your paper as well so that you see how they're supposed to be formatted. Because yes, the formatting is probably the biggest pain with these, if anything. All right, and now just to kind of give us a little bit of context, again, visualizing what it is that we just did. This is what that graph actually would look like if we did make that graph. And what we ended up looking at was this particular interval. So we're looking between the -2 and the -1 x values. And you can see that then boxed in which y values we are looking at. And so in that particular interval, in that little white box there, you can see that it does in fact have a root. It does cross 0 at some point, so it happens right there. And so that's what that told us. It didn't tell us where it was, but it did tell us that it happened somewhere between there. Now, we're going to go ahead and do one more of these just to practice this idea. I'd like you to go ahead and see if you can do this one start to finish. And of course, I'll be jumping in here and there as you're going in case you get stuck to give you a pointer about where to go from there. Now, as you've been working through this, I hope you started by thinking about finding that lower bound and upper bound. In other words, like what is f of 2 and what is f of 3. You actually want to find out what those values are. And here you can check that you got those correct. F of 2, you should have gotten 1. And f of 3, negative 16. Once you know that information, you should be able to go and write your conclusion. I suggest that you use the last conclusion that we wrote as a reference to make sure you're getting everything in there that needs to be in there. So this is how we would write our conclusion. Now, in this particular one, there's one little detail that was different from the last conclusion. Hopefully you're paying attention to it. Notice the order that I had to write these in. It didn't change anything else, but if I'm going to write them from smallest to biggest there, the f of 3 was actually the lower y value. It was the upper x value, but it was the lower y value. So I would want to list that one first when listing those out. Otherwise, it's the same basic idea as what we saw before in the last problem. And these two that we practiced with, both of these were finding if there was a root. So both of these were using 0 here. But I didn't have to do this just for a root. Like in this problem, I could have said, prove that there's a number, a value at negative 15, for instance, because that's still between our two values. I could plug in anything up here. As long as it ends up being between those two, it's still doable and it'll still be the same basic process as what we did for this one.